Hey students, welcome to part 3 on solving trigonometric equations. In this video we're going to look at some more complex trigonometric equations that involve, say, cosine squared or more sine and cosine. Think just a little bit harder difficulty level and see kind of how we look into that, and specifically how we can use factoring sometimes to help out with solving these. So in our first example here, we have the equation cosine squared theta plus 3 is equal to 4 cosine theta. And sort of our basic strategy for solving this equation would be to sort of treat it as if it were a quadratic equation, you know, like x squared plus 3 is equal to 4x, or in this case, because cosine squared theta is something we don't know, as is also cosine theta. So if you kind of pretend that that unknown is x, cosine squared theta would just be whatever that x squared is going to be. And that's sort of the key to being able to solve this type of equation, is treating it like that quadratic. So how we solve a quadratic equation is by setting it equal to 0 and factoring, or quadratic formula, but let's go use factoring for these. So essentially, if we're going to set one side equal to 0, we would, in this equation, it'd be easy to set the right side equal to 0, right? We could just subtract that 4 cosine theta to the left-hand side, and that would give us cosine squared theta minus 4 cosine theta plus 3 is equal to 0. So all I did was I subtracted the 4 cosine theta to the left side using the subtraction property. And you might be wondering, why did I put it in the middle? Just to go from squared to not squared to constant. Kind of like if we were writing x squared minus 4x plus 3, we would write it in that sort of order of decreasing power. But sort of so from here, after we set it equal to 0, the next step would be to factor this equation. And so if you're wondering, well, how do I factor equations with cosine? What's nice is they're going to factor the same way that an equation with x would factor. So if we look at sort of the synonymous situation, x squared minus 4x plus 3 is equal to 0. That's kind of my comparison equation. Or you could even make the substitution x is equal to cosine theta, but I'm going to skip that in this case just to save a little bit of work. But essentially we're comparing it to this quadratic equation. If we know how to factor the quadratic equation, the cosine equation over there on the left-hand side is going to be solved the same way procedurally as the quadratic. So how we factor this guy, as hopefully you should know if you're in precalculus, but would be x minus 3 times x minus 1 to factor that quadratic equation. And again, what that means is our trigonometric equation will factor identically to the quadratic equation. So in this case, our x takes the place of cosine, so it's going to actually indeed be cosine theta minus 3 times cosine theta minus 1 as the left side of that equation would factor. And you can go ahead and FOIL that out to verify, but cosine times cosine, so over there would make cosine squared, and then you'd have cosine times minus 1, which is negative 1 cosine theta, and then negative 3 times cosine would be minus another 3 cosine theta. So that inner product, if you're FOILing this, these two binomials out, would be negative 1 cosine minus 3 cosine, which actually make a negative 4 total cosine. And then finally, negative 3 times negative 1 would make positive 3. So basically, this is equal. This factoring works. If you FOIL it through, you should see that. And so your next question might be, well, where do I go from here? How do I solve each of these after we factor that? And the answer would be, well, again, the same as in the quadratic equation. So, you know, if you're thinking about the solutions to the quadratic equation as 3 and 1, you're right. But remember, the process for that is if we set each of these equal to 0, is called the zero product property. But basically, what we have over on that quadratic factored equation is x minus 3 quantity times x minus 1 quantity equals 0. Well, if either one of those two factors is 0, because 0 times anything makes 0. So if this guy is 0, it doesn't matter what x minus 1 is. 0 times anything is 0. Same goes for x minus 1. If that guy is 0, it doesn't matter what the first one is. Anything times 0 would still make 0. So essentially we have two separate solutions to that equation from each factor. So back to the trigonometric version over here, how we solve it is we set each of these two factors now we set each of those equal to 0 and solve each of those independently, assuming it has a solution. So we take this one, set it equal to 0, and take that one. So we need to figure out where is cosine theta 3 and where is cosine theta 1, assuming they could be. So what I would do would be just rewrite it as kind of a new equation with two separate solution paths. We'd have cosine theta minus 3 is equal to 0. And from this one over here, we'd have cosine theta minus 1 is equal to 0. And so from here, we're just going to solve them. So for cosine theta minus 3 equals 0, we could add 3 to both sides. That would give us cosine theta is equal to 3. And you should hopefully see a problem with this. But remember, cosine's the range of cosine, because it goes up and down, goes between negative 1 and 1. Cosine theta can never be 3, the normal cosine function. And if you try to take the inverse, cosine inverse of 3 is no solution, doesn't work. So this solution path actually has no solution over here. However, that doesn't mean our entire equation does. Just this particular factor can never be 0. Cosine theta minus 3 just can't be 0, that first factor. So as for the second factor, cosine theta minus 1, we could add 1 to both sides. We get cosine theta is equal to 1. And we could reference our unit circle to see, well, where is cosine theta equal to 1? Remember, cosine theta is at the x coordinate. And there's only one position where cosine theta is equal to 1, which is at 0. So only one solution over here, which is 0. So that would be our answer. Theta would be equal to 0 in this case. And we could add 2 pi k, remember, to generalize that. Because if we look at this particular equation here, these are just like the ones we're solving in part 1. These all have infinite solutions. So if we're trying to compensate for every single solution, it would be plus 2 pi k. So anyways, our final answer would be theta is equal to 2 pi k. And this would give us all the solutions to our original equation as a whole. So there we have it. And again, this first path, our first factor had no solution, which is not typical with a normal quadratic equation, but with a trigonometric equation can be the case in this one. And so at the end of the day, we have all these solutions. And let's quickly verify that that this makes sense in the original equation. So our solution was 2 pi k, which means, and remember, k can be any integer value, so 0, 1, 2, so forth. So let's say 0. 0 was our original solution. Let's check to make sure 0 works in the original equation. So if we look back to cosine squared theta plus 3 is equal to 4 cosine theta. If we're going to plug in 0 into here, we'd have, well, cosine of 0 plus 3 should make 4 times cosine of 0. Well, cosine of 0 was that spot we were just looking at. Cosine of 0 is 1. So we would get cosine of 0 is 1. So cosine theta squared would be 1 squared. So we'd have 1 squared plus 3 on the left-hand side. And then cosine of 0 is 0. So if I plug in 0, that would... sorry, cosine of 0 is 1. So if I plug in 0 there, that would give me cosine of 0 is equal to 1. And so what we'd end up with is 1 squared plus 3, which is, of course, 4, is equal to 4 times 1, which is 4. And so it does check out. And you'll check it if you check every other k value, like 1, 2, 3, you would see that 2 pi is the same position as 0, so that will also work, check out exactly the same as with 4 pi and 6 pi, and yada yada. So basically here we have it. This is all the solutions to our trigonometric equation. And with these sort of more complex equations, they can actually have a plethora of different solutions. It's, in this case, it was just one single answer, but they can have lots and lots and lots of solutions based on the difficulty level of our equation. And so if you look at the graph of your equation or try to solve it graphically by graphing both sides and examining the intersection, you can double check to see if your solutions are kind of in the right ballpark. And we can do that with our next example. So let's do one more example. Let's say we're trying to solve the equation. Let's erase this guy here. 2 times sine of theta times the cosine of theta minus cosine theta is equal to 0. And so in this example, one side is already 0, so naturally we could try factoring. And in this case, you might notice that there's two terms, both of which have cosine, and so that would be called our GCF. So just like if we had 2 times x minus x, we could factor, or 2 times x times y minus x or something. If there's an x in both your terms, you factor it out. So since there's a cosine in both of the terms in our equation, we can factor that common factor out front as cosine theta out front, and that would be times whatever would be remaining by the distributive property. So if we factor out cosine, what we'd have left from the first term would be 2 times the sine of theta. And from the second term, if we factor out cosine from minus cosine, well, we just have minus 1 left over from that second term. And so just like from the previous example, now that we have it factored, we'd set each factor equal to 0, and that will give us our individual solution. So we'd have one solution path if cosine theta is equal to 0, and we'd have another if 2 sine theta minus 1 is equal to 0. And then we'd solve each of these independently. So cosine theta is equal to 0. Well, cosine is 0. Remember, cosine is x. So we would have cosine is 0 right here at pi over 2. Right there at pi over 2. And cosine is also 0 down here at 3 pi over 2. So there's two positions where x is 0 on the unit circle. So those would be theta being pi over 2 and theta being 3 pi over 2, the top and the bottom of our unit circle, and generalize it by adding 2 pi k, which includes all solutions beyond the unit circle, or for all coterminal solutions of those. And then, so over here, 2 sine theta minus 1 is equal to 0. Well, we could isolate the trigonometric function, meaning we could add 1 to both sides and divide by 2 and solve this guy. And this is an example we did in part 1, but sine theta is 1/2 in 2 positions on the unit circle. Sine is y. So sine is 1/2 up here, and sine is 1/2 sine is 1/2 there at 5 pi over 6 and at pi over 6. Remember, they're always symmetric, but we get 2 theta values from this one. We get theta is equal to pi over 6, and theta is also equal to 5 pi over 6. And again, we could generalize by adding 2 pi k to these. And this would be more solutions. So in this particular equation, it had a whole bundle of solutions: pi over 2, 3 pi over 2, pi over 6, 5 pi over 6. Also plus 2 pi k to generalize beyond the unit circle. But there was four independent solutions just on the unit circle: pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. So if we're solving it in that interval, if we're solving it in the interval 0 to 2 pi, like sometimes homework will ask you to do, you would come up with actually 4 for just this one little equation. And again, you could try plugging it back into the original equation up here to make sure each of those works. Takes a little bit of work, or use your calculator to do that as well, to verify. And so, just as a last little exercise, I want to show you kind of what this would look like in a calculator, and how you can kind of compare your solution to make sure that it works. So let's pull up our TI-83, and I'm going to graph this equation in my calculator. So I'm going to make sure I'm in radian mode for this, because normal trig equations we solve with radians and we graph with radians, because degree mode, if we're graphing one period of the function in degrees, it takes 360 degrees for a trigonometric function to complete a cycle. And that would be a long period of time, 0 to 360. But in radians, 0 to 2 pi is not that far, 0 to 6.28. So it's usually just easier to graph in radian mode. So anyways, if we graph our equation, we have 2 times the sine of theta. And remember, normally our calculator uses x, same thing though, times the cosine of x minus cosine of x. And so this is our equation, and it should be equal to 0. So if I graph this, what I'm looking for if I'm solving it graphically is when does my curve cross the x-axis? When is it equal to 0? Because what I'm going to graph is the curvature of this function, and to solve the equation, I'm looking for when the curvature is equal to 0, which is on the right-hand side. So to graph this, we can use zoom trigonometric functions. So zoom trig, if you hit zoom and then go to number 7, which is zoom trig, it'll do it naturally on a trigonometric axis. So what it will graph from is negative 2 pi to positive 2 pi. You see this equation looks a little bit funky. But if I, those 4 values that I circled in blue were the ones from 0 to 2 pi. So I'm just going to adjust my window, which is actually right now it's going from negative 2 pi to 2 pi. But I'm going to change it from 0 to 2 pi, which just will graph one sort of cycle of sine and cosine, one period. And it will identify, I just want to make sure that those 4 values in blue are all seen as part of this graph. So basically, when I look at the graph now, I'm looking and I notice that it crosses the axis 1, 2, 3, 4 times, which is good because I got 4 sort of unique solutions from each of those 2 solution paths that came from the factoring of it. But what you might notice is that, well, all of these, this one, and this one should line up with those solutions I got. So if we look at it, remember the one I'm graphing from 0 to 2 pi. The one in the middle should be pi, which means this one should be pi over 2, this tick mark on my calculator. So this one's pi over 2 since this one's pi. And that's one solution, which would apparently, it looks like to me at least. So pi over 2 is there. Half of pi over 2 is pi over 4, which it looks like it crosses right there. Well, that it might not be exact, but if I look at my other solution, pi over 4 wasn't a solution, it was actually pi over 6. So this little guy right there should be my pi over 6. This is pi over 2. This one's my 5 pi over 6, which is slightly less than pi over 2. And then finally over here, between pi and 2 pi, right in the middle, between pi and 2 pi is 3 pi over 2, right there. So that guy's my 3 pi over 2. And basically these 4 different places where it crosses are those 4 solutions in blue. And it should line up in this case. We should have the same number of intersections with our axis as we have solutions. And of course you could use something like calc. You could calculate all those zeros using your calculator as well. So if you don't believe me that those 4 are those 4 solutions, which I mean you don't have to, but I'm a math teacher, so you probably should believe me. But of course, you should figure it out for yourself. But if we go to second calc 0 on our calculator, and we want to figure out one of these zeros. So let's say we wanted to figure out what this one is here, and that's the one I'm saying was 5 pi over 6. But if we look at this solution right here and calculate the 0, remember you have to find the left bound, the right bound, and your best guess. So you have to hit enter 3 times, once to the left, once to the right. And I said no signs change, so I think I messed up what I plugged in there. Let me try that again. Second calc, and then we go 0. So left bound, I'm going to go to a little bit to the left of the point of intersection. Right, I'm going to go a little to the right of that, and my best guess is going to be as close as possible. There we go, that fixed it. So, and what it's giving me is that 0 is at x is equal to 2.61799939. So, again, you wouldn't know what that value is if you're just winging it without any of this work over here. So all this algebra was needed to find it exactly. Our calculator can estimate those solutions with literally no work required. But if we want to know what that one is, well, we would have to do a little. You'd have to know how we got that. But anyways, this one's 5 pi over 6, and we can check to make sure that 2.61 is 5 pi over 6. So if we just type in 5 pi divided by 6, we could figure out this irrational number 2.617799, which is exactly that same position. So, and you could do the same with the other ones as well to verify all those. So anyways, you can use graphing to solve trigonometric equations, as difficult as it possibly could be, but again, you're going to be a little limited in actually finding the exact solution. And of course, a trigonometric graph like this is just one period of the function. It's going to repeat itself forever. Like if we go back to zoom standard, you can see that, I mean, just like a normal sine wave is going to go on and on, this trigonometric function is going to just keep on mowing over and over again. And remember, those plus 2 pi k's account for the periodic nature of these things, the complete repetitions. So even though that you see this thing crosses the axis many, many, many times, if we kind of look at just one period of the function, find all of those, which are those 4 solutions in blue, and then we add the periodic nature to that, which is plus 2 pi k, which repeat, get the repetitious solutions. We can basically just get all of those solutions, identify the patterns, and try to write that as simply as possible. And that's kind of what we do when we add 2 pi k, is just getting those repeated solutions. So hope you learned something, and if you have any questions, please let me know in the comment board, or click like. Subscribe if you like math and you want to see more math. I'll be continuing to post more as time goes on. Thanks for watching. Bye.